science gallery. Yeah, so Scott, take it away.
All right. Okay, well, we'll start my microphone on. Thanks, Brendan.
There we go. Thanks, Brendan. Well, welcome to the planetarium, everybody. My name is Scott Young, and I'm the planetarium astronomer here, and former member of the RASC Winnipeg Center. It is an awesome precision piece of mechanical engineering. We'll create the stars for us. The clockwork stuff in the center provides basically all of the motions of the solar system and gives us the ability to see the sky in a way that's really sort of unparalleled. Now, for those of you that are in the planetarium, using your mobile devices, you will see that your heads are silhouetted up onto the dome, because of course we're a little dark in here. So Marvin here can create the constellations, the stars, the planets. It's got 154 lenses in it, several large arc lamps to provide these bright views of the stars. The problem with Marvin is that all Marvin can display is what was known to the ancient sky gazers 5,000 years ago. The stars, as we can see them, we can fast forward through time, we can rewind, we can go through precession, we can go through all of the motions of the heavens, but astronomy has grown a lot in 5,000 years, certainly since the invention of the telescope. Marvin can't really show any of that stuff, and so we have always here in the planetarium used subsidiary projectors, secondary projectors, to show other things, close-ups of the planets, for example, or zoom-in views of deep sky objects, all that kind of stuff. And of course, as we started to go to other planets, those great spacecraft images of other worlds. When I started here in 1990, those subsidiary projectors, or secondary projectors, were all slide projectors. And there was something like 100 slide projectors all ganged together. And the machine gun sound of them resetting at the end of the show was known to sometimes make children cry because it was just so loud. We updated to video in about 1988, and then we started using computers to actually synchronize some of these projectors for us. If you remember what your computer was like in 1990 in terms of power and capability, obviously we've come a long way too. So about 4 years ago, the lights pretty much went out on Marvin. We really do not use Marvin as a primary projector anymore. We turn him on for special occasions. We use him for our astronomy course, where we're really trying to get people to see what the real night sky is like. But for most of our educational programs and for all of our public programs, we are using our new system, which is called Digistar. So the Digistar system is basically a giant video projector, well, 2 video projectors that covers the dome with a 2K by 2K image. And we'll just get that all fired up here. Bring Marvin out of the way. The great thing about a digital image, of course, is that you don't have to display only dots where holes have been drilled in your projector. You can display any kind of video image. And so, you know, we can add the view of the city here. We can show movies. You can hook your PlayStation up to this. Not that we've ever done that. Halo 4 is awesome on the dome. But the main thing that we use our Digistar system for is still the same thing that the planetarium has always been for, which is to simulate the sky and to give people a sense of what's out there so that they can go hunting for these things themselves. And that's always been the planetarium's mission, and it continues to be our mission. And so we're going to give you, even though many of you are probably somewhat familiar with what's up in the sky and how to find things, we're going to give you a little taste of the things that we do here using our Digistar system. And then we're going to move on to see one of the planetarium shows that has been one of our feature shows recently, the search for extraterrestrial intelligence. So we'll start off here. We've got the sun over there in the west. We've still got the green arrow to point, for those of you that remember the green arrow. The sun's way over there in the west, and we will let the sun set, we'll let the stars come out, and we will see what the July sky can show us as we wait for the sun to go down and the stars to come up. So here in the city, of course, we still have all the light pollution around us, but you can still see some of the brighter stars. And let's face it, most of us who aren't amateur astronomers get most of our sky views from inside a city. So it's a pretty useful place to start here. We will, of course, be able to point out the constellations and those kinds of things. We always start with the Big Dipper because it's the one thing that we can guarantee that almost everyone that has visited has seen. And the Big Dipper right now is over in the northwest, and we've got the lines that connect things. We used to have to do this with a slide projector, and the slide projector had to be perfectly aligned every day before the show, and it was a real pain. Now, we just press the button, and it's nice. So right now I'm running the entire show from an iPad, and basically the entire interface runs through a browser, so you can pretty much run these remotely. In fact, we had someone from Edmonton run a show for us here in the planetarium, and that's worked fairly well. In addition to the standard lines, we of course have all the constellation artwork, whether it's the Big Dipper or whether it's Ursa Major, the Great Bear. They all fit together up there. And turning on the different variations is just as simple as pressing a button here on the iPad. Now the key to finding things in the sky, as most of you again are familiar with, you start with one star and you draw lines through the stars and you draw to find some of your other landmarks, things like the pointer stars that point to Polaris, the North Star. There we have Polaris over in the northern sky. Polaris, of course, being the North Star, very close to the North Celestial Pole, the center point of all the motions of the sky. And this is something that surprisingly people are still unfamiliar with. A lot of people will come in and think, oh yeah, the North Star, that's the brightest star in the sky. Well, no. In fact, it's not even very easy to see in most cases. But if we crank on the fast forward here and we just let the sky start to rotate, not too fast because I don't want you to get sick until later in the evening, the North Star stays almost exactly fixed there above the northern horizon. Everything else spins around it. Of course, eventually the sun will come up. The stars will fade away as the sun comes up, and but if you could see the sun, or if you could see the North Star, it would still be in that spot. And everything basically moves in the same kind of way. So far, we haven't done anything that Marvin couldn't do. And in fact, Marvin's stars look a little bit better than our digital stars, so we really haven't shown off any of the capabilities here of Digistar. But we'll wait for the sun to come back to its sunset, and then we'll show the capabilities. Because of course, with this being a digital system, we have a digital universe in the computer here. Basically, all available astronomical observations that have ever been made have been put into this database called the digital universe, and all our planetarium system now is a way to navigate through that database and to visualize it. So everything that has been observed is in here in some format. And so we can stay here on the Earth, we can go to the other planets, we can, the day that Pluto came through with its planet, New Horizons went through the Pluto system, I guess 2 years ago today. We had those images mapped onto the globe of Pluto an hour after they came down here to Earth, because the digital system just sort of updates those things very, very quickly. We're just going to go to a slightly darker sky. We'll get rid of our city lights and see what we can do here with. So the thing that really works well with the Digistar is the sense of perspective you get. When you're here on the Earth, looking up at the sky, we see the constellations as flat pictures, just dots and lines. We see the Milky Way as the band of light that goes across the sky, the backbone of night. And we see things as if it's a dome around us. But of course, the universe is 3D. And to be able to see that, we need to be able to move throughout this database. So we're just going to make it a little darker here. We're going to head a little farther south to give the Milky Way a nice view here, so that we have a nice view of the Milky Way. Now, the Milky Way, of course, here we're exaggerating the contrast. This is the kind of view you might get if you had perfect vision and very, very dark skies. But this is not the full view of the Milky Way. This is just what our eyes can see. There are multiple wavelengths that we've observed the Milky Way in, and all of these data systems are all built into the planetarium. So if we want to see the H-alpha, the hydrogen clouds throughout the Milky Way, we can do that. Or if we want to see the far infrared view, we can see what our eyes would see if we could view that infrared part of the sky. A very different view of the Milky Way. My favorite one, I think, is the gamma ray view of the Milky Way. It's not as high resolution, but it really doesn't look much like the Milky Way at all that we see at night. All of those dust clouds and the sort of vertebrae of the backbone of night are gone, and it just looks like a line across the sky. Basically, it looks like an edge-on galaxy, which of course is what it is. But our visual view, it's a little bit harder to see that, especially when people come in and they don't really know anything other than this. They think, oh yeah, the Milky Way, that's that band of light in the sky, if they've even seen it. And then you tell them that the Milky Way is a spiral galaxy, and show them a picture of a spiral galaxy, and they don't really put those two things together, because you show them separately. Well, now what we can do is we can just move from one place to another, and without turning off one picture and turning on the other, we can actually just fly above the Milky Way. And we'll just let our computer catch up here as it does a little bit of calculation. So we just fly south out of the plane of the Milky Way galaxy, and this is our Milky Way as seen from below, essentially. And the little circle is a 1,000 light-year circle centered on the sun. So this is the part where you all feel small and insignificant. Now, of course, astronomers have not mapped all 150 billion stars or so or 400 billion stars or so in the Milky Way galaxy. So some of them are made up by using the theoretical models of how dust and gas and stars would be distributed in a galaxy of our type. So when data doesn't exist, the gaps have been filled in using the sort of extrapolating from the latest scientific knowledge. But where there is real data, then we use the real data. Take a little perspective change here. We'll just fly past some of the globular clusters, which are all those little fuzzy things around the core of the galaxy. Beautiful to look at in a telescope, one of my favorite types of objects. A lot of people say they all look the same, but they really don't, especially if you crank up the magnification and take a look at these things. And especially now is a great time, July and August. We've got so many globulars up there to enjoy. Just move one more perspective here and take a look at the Milky Way as the edge-on galaxy that we saw it from before, but still looking at it from the outside. Lift things up a little bit higher here. So here's our edge-on galaxy, the Milky Way, with all the globulars around it. A couple of satellite galaxies down below there. For those of you that don't have Marvin's head in your way, there's the small and large Magellanic Clouds down there. And this is really, when you can see it this way, it really does look like an edge-on galaxy. And then when we just zoom in back towards Earth, we actually just fly inside and it's like, oh, that's what I'm looking at when I see that fuzzy band of light. All I've done is move inside it, and we can see the Milky Way galaxy from the inside. We've found that from the old system, when we would do these shows and then ask kids afterwards to explain what they learned, to the new system where we can do this all in one seamless image, that people get it. The aha moments have more than doubled from the old system. So that's a pretty useful thing. People seem to really understand some of these concepts a little bit more effectively when we're using the digital system. And of course, because it's all digital, you can literally just take a joystick and fly around in the universe. And when you get that hands-on ability to sort of play with the universe yourself, you really get a good sense of how things fit together. And we're just going to do a wipe here for a second and go to the evening sky again, because we want to cover a couple of the things that are up. And I know that Mick is going to be talking a little bit later on about eclipses and things like that, so I'm going to confine myself to talking a little bit about basically what's happening in the evening sky right around now. So after the sun goes down, and actually we'll rewind just a little bit here. After the sun goes down, you can still see Jupiter fairly high in the southeast, even before it gets fully dark. It's quite a nice view. Even though it's starting to get low down in the sky, there's been some amazing stuff with Jupiter going on. Of course, Juno just flying by there recently and getting some close-up images. And Jupiter is a fantastic planet to look at through a telescope. It's probably the one thing that almost never disappoints. And seeing the cloud bands, seeing the moons, the Galilean moons do their little dance back and forth night after night, even in a small telescope, it's a pretty impressive sight. But you pretty much have to catch it soon after it gets dark. Now, it doesn't get dark until after 9:30, 10 o'clock already anyway, so we're talking fairly late into the night. We're still in that period where we're barely getting any actual dark skies at all. But we'll fast forward to the point where we do have some dark skies. I've done more summer observing this year than I have in many years, and that is almost solely because there have been no mosquitoes, or very few mosquitoes. I cannot stand the mosquitoes. I can't dress for them enough, and even the sound of it drives me nuts. So that has kept me out of my summer observing for the last number of years, but this year's been great. I've been out 4 or 5 nights in the last month or so, and it's just been glorious. I used to be very regimented in scanning the sky and planning what I'm going to do in advance and things like that. Now I just take out my wide field scope, and in the summer I just scan the Milky Way and discover things and then go and look them up afterwards to see what they are. It's a pretty fun way of doing things rather than going for particular targets, because you often happen across something that maybe on paper the book says, oh, that's probably not going to be impressive in your telescope, or you're probably not going to see that or whatever. But that's not always correct, and sometimes you come across these gems that you just wouldn't see otherwise. So Milky Way is really the highlight of what's going on right now, and you really get a good sense of the variety of objects that there are throughout the whole area. Lots of nebula, lots of globular clusters, lots of open clusters. Now we're just at sort of last quarter moon, and that means in about a week or so we'll get into that wonderful new moon period where we have nice dark skies for the whole night. So that'll be a good, well, for the whole night, as long as the night is 2 hours or so. But that means it's a great time to get into the dark sky locations. There are a couple of planets to look for. Saturn is still coming up quite low, but still visible, coming up later in the evening. And, wait a minute, sorry, let me get the labels on. And just before dawn, we have Venus again starting to dominate the morning sky. The 2 unlabeled circles up there, those are Uranus and Neptune. They're pretty well placed to try and track down if you're going to be up fairly early, but they're a little bit more difficult unless you know what you're looking for. They're way smaller even than you're led to believe just by reading in the magazine. You really need to have a good night where you can crank up the power to really resolve those discs. Although the color is pretty striking, so that can make it really fun and interesting to observe. So as we go through an entire night, there's still lots of great things to observe. The summer really is, like I say, with mosquitoes gone, the summer is a great time to do a lot of great telescope observing. I just got a new camera too, so I've been trying that out, and it's amazing what you can do with just a very simple camera nowadays. I'm rediscovering astrophotography for about the 4th time in my career. And this is a great time to do it again because the wide field Milky Way shots are really, really good. But I'm going to be spending the next month trying to figure out everything that I need to take down to the eclipse because, of course, we're coming right up to that eclipse time. And that is really the major event of the summer. Is there anyone here that is driving down to the eclipse? Yep, no, nobody. I can't see your hand, so I guess you could just say yes. Yeah, there we go. Okay. Yeah, Nebraska. Okay. Who else is going to Grand Island, Nebraska from here? Anybody?
Yep.
Yeah? Okay, cool. Excellent. Wyoming? Okay, well, that's fine. I used a very technical system to choose where I was going to go. The day that I started thinking I better book a hotel, my friend Paul Gray from Nova Scotia posted on Facebook saying, "Hey, I just booked a campground in Grand Island, Newfoundland, or Grand Island, Nebraska." And Paul's a really dedicated guy. I know he does his homework, so I booked in the same spot, and that was good enough for me. But now it turns out there's about 50 RASC families coming from across the country, and so we have a good chance to visit with all of these folks because I haven't seen some of them for years, so I'm really looking forward to the trip over and above just the eclipse itself. Now, one of the things I wanted to show you before we move on to the planetarium show segment is what I would call, what we call the orrery, basically the model of the solar system. We've got the sun and the earth and the planets and things like that. When you start to look at the solar system from above, you get a very different view, of course. And I just wanted to give you a little bit of a view here of the solar system, along with one of the newest members of the solar system, which we're just going to add in here as we start to zoom out. Many of you may know local Senator member Stan Runge. Just had an asteroid named after him. Yeah, we've tried to send him into space. That's actually too expensive. But that blue circle there is the orbit of asteroid Stan Runge, which just recently has been named after our own Winnipeg Centre member. And we found out about that about noon today, so we just popped in the orbital elements and threw it up there. In fact, we can even fly to Stan Runge. And let's get a very good close-up of Stan Runge here. Here we go. It's just a dot. It's actually quite a small asteroid until you start getting in close. There we go. Let's see, lumpy, no hair. Yeah, Stan. Okay. Actually, this is, of course, we don't have an image of Stan's actual asteroid at this point. It's quite small, and there isn't a detailed image. So this is a simulated one based on the reflectivity and the albedo. It should be about this size. But it's pretty impressive to have one of our members have an asteroid named after him, and well-deserved because Stan has been a fixture of the astronomical community for about 307 years now. So congratulations, Stan, for the honor, and it's great to see. Are you here, Stan? Is Stan out there, or is he not?
Probably not.
Probably not. Okay, well, we'll tell him that we laughed at him.
For those who don't know, Scott Young has one named after him too.
But I'm not a Centre member, so I didn't bring it up.
You were.
I was, yes. So what we're going to do now, I could basically play with Digistar for hours, but I just came off of 2 weeks vacation, and I'm a little bit rusty. So we're going to move on to the programmed portion of the show here, to one of our feature shows, which is narrated by a good friend of mine who's having a birthday today, Harrison Ford, and he will be narrating the show here. It is, the show is called The Search for Life, Are We Alone? And of course, this is the ultimate question. This is something that even if you're not thinking about it consciously when you observe the sky, you just can't help but wonder, are we alone? Now, many of us have very strong opinions on the answer to that question, but none of us have the actual answer yet. And it's amazing that we live in a time. When I was taking university, I just discovered that, sorry, an aside here, Mick and I took second-year astronomy together in 1989, and I was thinking back to 1989 and what we knew about the search for life out there. We had the Drake equation, and we had a whole bunch of people thinking, oh yeah, there must be aliens, oh yeah, there's no aliens, but there was no evidence. We hadn't found extrasolar planets, we hadn't found anything yet. And from then to now, the number of worlds that have been discovered, the number of worlds in the right zone for possibility of life, just the idea that all these worlds out there truly exist, they're not just theories anymore. It's just amazing that we live at this time when the answer to the question, are we alone, might actually be answered. That's pretty awe-inspiring. So I'm going to let my buddy Harry tell you about it, and after the show, we will answer any questions that you might have or do any more things here in the planetarium. Then we're going to take our break, and I'm going to do some technical setup for the other presentations that will happen after the coffee break. So right now, just sort of sit back and relax, and I will let you enjoy The Search for Life. Are we alone?
Listen. Listen to the sounds of our world. The earth is so alive. Hello, I'm Harrison Ford. Beautiful night, isn't it? You really have to get away from the city lights to see the sky like this. That band of light crossing the sky, that's the Milky Way. So many stars. You know, the stars are really other suns. They're just very far away. You can't help but wonder, are there other worlds like ours hidden among those stars? And do any of them have life? Is there someone out there lying awake, wondering if we exist? What would they be like? It's hard enough to imagine life on Earth. If you've never seen one, could you imagine an elephant or a lobster? On our planet, life is everywhere. But can life exist anywhere? We once believed that all life needed sunlight, but we were wrong. This place is as alien as another planet, but it's right here on Earth, at the bottom of the ocean. When we finally got down to the deep sea floor, we found another kind of life that doesn't need sunlight. Miles below the surface, there was life where no one thought it could be. Here, in this endless night, life feeds on scalding volcanic fluids that erupt from the molten depths of the Earth itself. If the sun ever stopped shining, life here would go on, sustained only by the Earth's inner heat and chemistry. Life is tougher than we thought. If life can get along without sunlight, is there anything that life just can't live without? On Earth, all life as we know it needs liquid water. But could there be other kinds of life that we don't know? Are there creatures on other worlds who can't stand water, but crave, say, ammonia? Could be. If life teaches us anything, it's that we've got to keep an open mind. So far, we know of only one world with life, the Earth, our own watery blue planet. Our neighboring moon is bone dry and lifeless. The Earth orbits at the right distance from the sun and has the right kind of atmosphere to allow liquid water on its surface. In our solar system, Mercury and Venus orbit closer to the sun. They don't have liquid water or life. But what about Mars? The next planet out beyond Earth. In some ways, it's a lot like home. Mars has a 24-hour day, regular seasons, polar ice caps, and dust storms. It has the biggest volcano in the solar system, 3 times higher than Mount Everest. In the past, Mars was probably even more like Earth than it is today. But now the surface is a barren desert. The Martian air is so thin and cold that any exposed liquid water would instantly evaporate and freeze at the same time. So if there is any life on Mars today, it's below the surface. Mars has enough heat and pressure below ground to keep water liquid. For all we know, Martian waters could be flowing through an underground network of pores and cracks full of microscopic creatures. Let's go down to the actual surface of Mars. We can see it through the eyes of NASA's Pathfinder spacecraft. You are now as close as anyone has ever been to walking on Mars. If we never find a trace of life on this world so like our own, then life may be rare in the universe. But if we find any kind of life native to Mars, no matter how tiny, then life must be in lots of other places. Beyond Mars are the giants of the solar system, the gas planets. All of them have moons made of rock and ice. Jupiter has 4 giant moons. One of them, Europa, may be the best place in our solar system to look for life. Its fractured icy crust floats on a deep ocean of water. Volcanic hot springs may be gushing from the sunless seafloor of Europa and feeding life, just as we saw back on Earth. If there is life on Mars or Europa or anywhere else inside our own solar system, we may be close to finding it. But what about life outside our solar system? The stars are millions of times farther away than the planets of our sun. If you could look back at our solar system from the distance of a neighboring star, from so far away, the Earth and its fellow planets would be lost in the sun's glare. In the same way, the planets of other stars are invisible to us, but we can still detect them. When a planet circles a star, its gravity causes a tiny wobble in the star's motion, telltale evidence for an unseen planet. Until a few years ago, the planets of other solar systems were only theory or science fiction. But now these so-called exoplanets are a scientific fact. We found the first one in 1995, around a faint star called 51 Pegasi. Soon we found another, and then another, and now we're finding about one a month. This is a revolutionary discovery. Planets could well outnumber the stars. We don't know yet if any of those planets have life, but we do know they have something in common with our Earth. All those planets were formed by the same cosmic process. If we could see it from outside, our Milky Way would look like this: a vast spiral galaxy with hundreds of billions of stars and maybe 1 trillion planets. That's right, 1 trillion. Where did all those worlds come from? Let me tell you a story of one of them, our own. It began in a galaxy long, long ago, nearly 5 billion years ago. That may seem impossibly remote, but there's an unbroken thread that connects each of us, you and me, and all life on Earth, to the awesome events of that distant time. Back then, there was no sun, and no Earth. Our galaxy was flashing with the massive explosions of dying stars, blowing themselves apart. vast clouds of gas drifted through space. The exploding stars stirred up the clouds and enriched them with atoms of carbon, oxygen, iron, and all the other elements. Within the clouds, these atoms were forming grains of dust and ice and organic molecules, the building blocks of planets and life. We're made from this stuff, this star stuff, and it's everywhere. In the depths of the clouds, a brilliant young star illuminated a clearing trillions of miles across. Near the edge of the clearing, smaller clouds collapsed, which made them denser and hotter. When they got hot enough, they became new stars. And one of them was our sun. For a few million years, our newborn star was surrounded by a spinning disk of gas and dust, the leftover debris that made the planets. Within the orbiting disk, grains of dust and ice stuck together to form clumps. These snowballed to form rocky asteroids and icy comets. The largest asteroids grew by colliding with the smaller ones, sweeping them up to become the inner planets of our solar system. And one of them was Earth. Bombarded by leftover asteroids and comets, our planet had a violent youth. But when the bombardment tapered off, life got started. We don't know how life began on Earth, but as soon as life was possible, it was there. Once life took hold, it began to change the planet. Green plants appeared and supplied oxygen. Animals evolved that could eat the plants and breathe the air. And some 4 billion years after life on Earth began, we humans awakened to consciousness. We began to understand that the story of the universe is our story. We looked up at the stars and we wondered. We learned that the same process that made the Earth has made billions of other worlds in our galaxy. So what are the odds that our planet is the only one with life? What would the worlds of other stars actually look like? So far we can't see any of them close up, but we can speculate. There could be gas giant planets lit by 2 suns. orbited by giant moons with oceans and islands and continents of their own. And who knows, maybe life. At this very moment, someone on a planet of another sun might be looking towards the Earth and asking, could there be life on that little world? In fact, we on Earth reveal our presence to the whole Milky Way. Our radio, television, and radar waves are spreading out into space at the speed of light. A radio broadcast of 60 years ago has by now traveled out to 60 light years in all directions. The expanding sphere of Earth's radio waves has already washed over many of the exoplanets we've discovered. And it will continue to spread out across the galaxy. Already, someone on another world may have picked up faint signals from a distant Earth. And we ourselves are searching the stars for signs of intelligent life, so far without success. But we've barely scratched the surface in our quest for other planets, for other life, and for intelligence in the cosmos. We think of our Milky Way as a galaxy of stars, just because the bright stars are what we can see. But now we know it's also a galaxy of unseen worlds. At this very moment, the same process that made our world is making new ones throughout our Milky Way. Making worlds is what galaxies do. And our galaxy is only one of billions in the known universe. So the possible number of worlds that may have life is staggering. Imagine what might live on all those worlds, each with its own epic tale, no two of them the same. Other life and other minds may dwell on countless other worlds. But nowhere else in 100 billion galaxies will we find another planet just like ours. All life on Earth evolved to fit the changing environment of this little world. It made us what we are. If we can learn to protect our only home in the cosmos and the life that it brought forth, just think of the new worlds and ways of being alive that we might discover.
And of course, in the 5 or 6 years since the show was produced, there have been even more discoveries. We have actually imaged individual exoplanets at this point, also, though still not close enough up to see some of those pictures that we might have seen in the show there. It's a great time to be following astronomy. Now, what we're going to do, I'm going to bring up the lights here. If anybody has any questions, come on over to the control console over here. I'll be happy to answer any questions. Otherwise, you can head out into the science gallery and enjoy some refreshments, and then we'll get set up for the second part of our meeting.
Just to use the parents trying to show up over there. I kind of introduced myself. I've seen a few new faces tonight. My name is Brendan. I don't really look like it, but I'm the president of the Winnipeg RASC. I do look exactly like the president. I've got the orange face. I don't have a tie. It doesn't run down past there. So, yeah, but I want to thank everyone for coming out tonight. It's actually, I don't know, this is really cool. I saw a lot of hands go up and they said they hadn't been here in quite some time, so that's really cool. I did also really want to thank Scott for letting this happen. I don't know if you guys noticed, but you didn't pay to get in or anything like that. And so I think this is a very good relationship that we have that Scott will probably be taking advantage of around Eclipse time if we can find anybody to stick around. But yeah, no. But I want to say thank you very much, Scott. This is really cool. Taking you back through our originally scheduled program, Nick will be talking about the Saros cycle as part of our beginner session. So, take it away, Nick.
Okay, well, Brendan says it's very nice to sit with the crowd here tonight. Now, before we talk about eclipse cycles or Saros cycle, I think we need to understand first, or describe what kind of eclipses are possible and what the causes of eclipse are. And then we'll see how much time we've got to see how much we can explain about some kind of repetitive patterns or cycles coming back. So eclipse cycles is the title of the talk. And basically the presentation outline is I'm going to give some examples of the type of eclipses as I mentioned. We're going to talk a little bit about the solar eclipse that's coming up on the 21st of August this year. We won't get a full total eclipse in Winnipeg, but I will talk about it because there will be certain things that will be visible from Winnipeg. Then I'm going to talk about what causes eclipses. And then we'll see if we can understand something about these Saros cycles, which are not easy to explain, but I'm hoping I can at least get the idea across that there are some kind of patterns that do repeat themselves in these eclipses. And then we'll show visual examples of this so you can appreciate how useful that Saros cycles are. And depending on time, we might even have time to have a quick look at the INEX cycle, which is another one even more complicated. Okay, so example of a total solar eclipse. There you'll see the moon, which is between the sun and the earth. Pointer is here. Here we go. Now this part here is the umbra, which is the full shadow made by the sun shining on the moon, but this part is in full shadow. And if the pointy end of the shadow would be below the surface of the earth, then on the surface of the earth you will get a little small area where you will see an eclipse. Now the eclipse will run from west to east. During the time that it's under the blue shaded area, you're getting a partial eclipse of the sun, and it's only on that little pointy part there where you can see the full eclipse, which will rip across the northern United States there. Now, this kind of eclipse can only occur when the moon is close enough to the Earth that it makes a full shadow over the Earth. See, the moon's orbit is slightly elliptical around Earth, which means there are times when the moon is close and there are times when it is far. So the moon has to be close enough so that the pointy end of that shadow, or the umbra, will actually make a shadow on the Earth there. The other kind of eclipse, now supposing the moon is a little farther away from the Earth, it's what we call the apogee, which is the farthest point from Earth. As you can see there, oops, sorry about that. What you'll see there is that the, no, come back one more. Get used to this, yeah, there we go. Now there you see the moon is farther away from the Earth, but the pointy end of the shadow doesn't reach the surface. So this area here, you'll see what's called an annular eclipse, or a ring eclipse, which means that the moon will come right in front of the sun, but because the moon is so far away, it won't cover the sun, So you get the sun as a ring around the moon like that, and that is called an annular eclipse. Now again, there's lots of areas there where you get the partial eclipse. Now if you can imagine, like on the first slide, where this pointy area was just on the surface, I said the eclipse will come across the planet from west to east like this. Now the distance where the eclipse begins is a little farther from the moon than when the eclipse is right overhead here. Now if this part, the first part of the eclipse is beyond the pointy end of that shadow, you will start off with an annular eclipse, then you might get a full eclipse, and then it will finish off with an annular eclipse again. And such an eclipse is called a hybrid eclipse. So we've got partial eclipses, we've got total eclipses, and we've got hybrid eclipses there. Now if you look at the moon, now the moon, the Earth is a lot bigger than the moon, so the umbra shadow is a bit wider to start with, which means it's not too difficult for the moon if the moon and the Earth and the Sun are all lined up, that if the moon goes into the shadow here, into the umbra completely, then it's called an eclipse of the moon. But if it doesn't quite go through the umbra, like this pre-umbra is like a cone that surrounds that area there, and the moon might only go through the pre-umbra, in which case you get a partial lunar eclipse. So we've got all those different kinds of eclipses that are possible. Okay, as you can see, it goes when the full moon passes through the Earth's umbra shadow, as we mentioned. Now here's the part of the eclipse that's going to happen on the 21st of August. Now you notice it probably starts on the Oregon coast there about 10:18 in the morning Pacific time, and then it exits South Carolina about 2:48 Eastern time. So because of the time change, there is only about an hour and a half before this eclipse is going to rip across the country there. It's really fast moving. But you notice too, at 1 o'clock Central Time, this area, this point here, is pretty much south of Winnipeg. And in fact, it's 12:57 is going to be the time of maximum coverage of the eclipse in Winnipeg on the 21st. Okay, so what we got now? Okay, I wanted to show you. This is the point of maximum eclipse by Nashville, Tennessee. There, that's the maximum length of the eclipse. It's going to be happening there. It does keep on way past into the Atlantic here. They've only shown it here up to the maximum eclipse. And these are pictures of what the sun will look like at maximum eclipse. And you'll notice here that at that time, we'll have a bite out of the sun on that side. And we have the lights, Scott, and where's Scott go? I need the lights.
I think you're okay, Mike.
Okay? Okay, well, can you see this okay?
Yep.
Okay, imagine this is the sun. Now you notice on these pictures, the moon is coming from the west-northwest down to the east-southeast. So it's actually dropping south very gradually across the sky as it goes. Now, since the moon is actually moving from right to left with respect to the sun across the sky, when the moon starts to cover the sun, it will probably start covering the sun like that. When it gets the maximum eclipse, the sun will probably look like that at 12:57, and then the moon will keep off going south slightly, and the last thing you'll see of the eclipse is when it's like that. Now we have to caution people, don't look at the sun without proper protection, otherwise you'll damage your retina. It's very tempting to take a quick glance to see, but you have to get the proper eclipse glasses or welder's glasses with at least as dark as 14 grade. There's no other safe way to look at the sun, otherwise just look at it on the television maybe. But for those who are interested, you know, this is what you're going to be seeing on that day. And here's another picture that shows you. Now again, this is showing you about 1 o'clock in the afternoon. Now you notice here, there's Lake Winnipeg. So Winnipeg is just there, very close to that. So what you're going to see is, you're going to see the sun looking like a hat over a big dark circle like that. You won't see this part of the circle, but you will see the bite taken out of the sun there. And that was pretty similar to the way I showed you, hopefully, as the moon crosses. Okay, now here's what the eclipse is going to look like. Like where you see that big blue shadow crossing, everywhere in that area you'll see a partial eclipse. And it's where you see the black dot cross, those are the areas that are going to see the full eclipse, or total eclipse. So you're very lucky if you could be in an area to see a total eclipse, because there's not much of the planet that it will cover at any one time. Whereas a lunar eclipse, because the whole night side, you're looking at the moon, the whole world on the night side can see a lunar eclipse, which is why they're much more common to see or witness. But the solar eclipse is quite rare. In fact, I think the next one in continental US or continental North America doesn't happen, I think, until 2045. So I don't know how many of us will be around then. Certainly won't be. Okay, there's an example of partial eclipse, like a bite taken out of the sun there. But we should try and understand what causes eclipse. Now the Earth, as we know, if you can imagine, here's the Earth's axis. The Earth is tilted about 23.4 degrees, and it's facing the sun for the northern hemisphere summer. The North Pole is facing towards the sun. When it's spring, it's going around the sun this way, so this will be fall over here. No, sorry, that would be winter. Like if the Earth is here, or the sun is here and the Earth's there, that would be winter. This will be fall, this will be spring, this will be summer, and this will be fall again. Now the interesting thing is, for many, many years, I was always under the impression that just like all the other big moons of Jupiter, Saturn, Uranus and Neptune, pretty well all the moons go around the equator, or very close to the equator. But I always thought the moon did the same thing as well. Now if that was the case, the only time that the moon and the Earth and the sun would line up is during the equinoxes, where the axis is like this, and you've got the axis of the Earth, moon, and then the sun, so they will all intersect. But what surprised me is when I found out that the moon, the plane of the moon doesn't sort of go around like the Earth does, so around the Earth's equator. The ecliptic is what's called the plane of the Earth-Sun plane. Like if you can imagine the sun in the center there, or rather the Earth, if you can imagine the Earth in the center of this wheel, and the moon is rotating where the tire is around the edge. The moon is actually, the plane of the moon kind of follows the ecliptic, but it's tilted about 5 degrees to the ecliptic plane there. So the moon is never very far away from the ecliptic. Now, what I'm just going to try and demonstrate one thing here, if I can. Now, you probably remember in school when we talked about gyroscopes and the 3 sessions of gyroscopes. Well, it's very easy to demonstrate simple precession like that, because you know the wheel will try and turn like that. If I hold it there, if I hold it here, it will try and turn around this way. But to try and demonstrate this over here, it's a little more complicated. Now, I'll see if I can get this to work. Okay, imagine that's the moon plane now, and you'll notice it's starting to tip down over here. Oops, it's going around there. I'm trying to make it sort of wobble around like a real orbit does, but it's pretty hard to show this. But you can see there, it's actually precessing a little bit in this direction. And that's exactly what the moon plane does as well, which means it's not going to be at the same point every year when it comes around again. Okay, so we mentioned that while the Earth is tilted to the ecliptic by about 23.4 degrees, the plane of the moon's orbit is only just over 5 degrees. So it's very close to the ecliptic. Now, when that plane of the moon, Earth plane moon, when it intersects the Earth-Sun plane, that point is called the nodes of the orbit. And when the moon is descending down through the ecliptic, it's a descending node. And when it's coming back up again above the ecliptic, it's called the ascending node. And those nodes have to be lined up with the Earth and the Sun exactly before you can get an eclipse. Okay, we mentioned that. Now this would happen about 2 times a year, very, very, very occasionally 3. Now I'll see if I can demonstrate this a bit here again. Okay, imagine this is the moon's sort of nodes here coming across like this. When they're lined up with the sun like that, you can actually get an eclipse. But as the moon rotates around, those nodes, after 1 year, after 1 year of the moon going around, about every 29.5 days, it will be slightly, that axis will be slightly to the right by about just a few degrees, which means that it won't be lined, it'll be lined up here just before it comes back to the start of the circle. Now, anytime you've got, within this range here, where you've got the nodes lining up, because remember, over here, the orbit will be like that, so when the moon is going around, it's not going to be lined up exactly. But these nodes have to be pointed to the center. Now, during that time, when they're roughly pointed to the center, we have what we call an eclipse season, which is about 34.5 days. Any time during that 34.5 days, if the moon comes down that way, you'll get an eclipse. And then just under 6 months later, you'll get another eclipse season. And then just less than 6 months later again, about here, you'll get another eclipse season. So it's not quite a year. And it's for that reason why eclipses can happen at any time of the year, but it takes quite a little while. It takes about 18.6 years for those nodes to completely do one rotation and get back to the beginning again. So it's a very slow-moving cycle, but it does actually help explain why we can see eclipses pretty well anywhere on the planet at any time of year. So I always used to wonder, well, how come we're not seeing eclipses near the equinox? Well, that's before I realized that the moon doesn't really circle the equator of the Earth. And in fact, all the major moons of Jupiter, Saturn, Uranus, and Neptune do follow the equator. Even Uranus, which is tipped on its side, the moons still rotate around the equator, not the ecliptic, eh? And the only other moon which is close to the ecliptic is the Triton moon of Neptune. And they believe that was like a captured asteroid because it's going around the moon the wrong way as well, but it's in the plane of the ecliptic and not in the plane of the planet's equator. And that's why people often used to think that maybe the moon actually was a captured asteroid, you know, at one time. But now the common theory is a little different, of course. Okay, we've already mentioned that. Usually 2 or occasionally. Okay, at each eclipse. Now, if the moon, when it's new moon, if it's within, I think, about 17 or 18 degrees of the node, you can get an eclipse of some kind, even if it's just a partial of the very north end of the planet or the south end of the planet. And in each eclipse season, because it lasts 34.5 days, you can get 2 or very rarely 3 eclipses. Now, when we say eclipses, we're also talking about lunar here. And the reason there can be 3 sometimes is just like people who get paid bi-weekly. Usually there's 2 paychecks per month, but once in a while, usually twice a year, you get 3. It's exactly the same reason why, if the new moon happens right after the eclipse season starts, you've got time for a full moon 2 weeks later, and then another new moon again, before you're outside of that eclipse season. So it is interesting, but I mean, that's why you can occasionally get 3. Because I remember once in Yellowknife, I was up there, we saw an eclipse of the moon, and then a month later we had another eclipse. I thought, wow, how can that happen? Well, anytime you can get 3 eclipses in the season, you can get solar, lunar, solar, or lunar, solar, lunar. But it only happens once in a while that you might get 2 eclipses, lunar eclipses together that you can actually see. Okay. There's an example showing, that's the descending node there, where it says node here. That is where the intersection of the moon's orbit is with the ecliptic, and that's where the node is. This is greatly exaggerated, this angle. That's way more than 5 degrees. It should be more like this. But we need to see this to show you, the geometry of what's happening. Like if the node is too far to the east. Now, when you're looking south towards the sun like that, east in the sky is to your left and west is to the right. So if the node is too far away from the sun like that, then it'll miss the sun completely and you won't get an eclipse. Now, let's say on the next time that the moon comes round, it's a little bit closer to the sun, and it's just clipping the northern part of the sun there as it goes across. So that will give you a partial eclipse anywhere. It won't give you a total eclipse anywhere, because the umbral shadow in that case will be going over the top of the Earth. And if the node is right on where the new moon is, like there, you'll get a full eclipse. So hopefully that explains. And when we say a full eclipse, that can be a total eclipse when the sun is totally covered by the moon and you get the beautiful corona, like in the opening picture of the presentation. Or it can be an annular eclipse, just like a ring. If the moon is far away and all you can see the outside of the sun around the moon like that. You can have those 2 types of eclipse, or you can get your, and in that bigger area, of course, you'll see a partial eclipse when that's happening too. So, rotation of the Earth, moon plane with respect to the Earth-Sun plane. Okay, when I tried to do that wheel experiment then, I tried to show you the precession of the orbit of the moon. Well, that red disk up there, don't take any notice of where the moon is. The only reason the moon is there stationary is to tell you that outside that circle is where the moon orbits the Earth there. Now this line across here, and I can't stop this picture once it starts, once I get out of the presentation, but when it's lined up now, here, here, and here, the nodes are lined up with the moon and the sun there. But that plane of the moon's orbit, even though it's only 5 degrees in reality, it does actually wobble around like that, but it takes 18.6 years to do a complete circuit. So one side of the moon will do like a half circuit, it's called like a SAR versus a Saros, which is well actually even that's not correct, but anyway, that gives you an idea of what the moon is doing. And the interesting thing about the moon couldn't care less whether the Earth is summer, where it's pointing towards the sun, whether it's winter pointing away, or it's equinox. It just does its own thing. It doesn't matter which way the Earth is facing, just that you do get eclipses whenever sun, moon, and the node of the moon, or one of the nodes, is lined up. You will get an eclipse. And I didn't mention it down there. There's the rotational period. And that means that every year that the moon goes around, those nodes will shift in the western sky by about 19 degrees. So that's why it'll be lined up with an eclipse again before the full year is up, because by the time it gets around to the full year, it's already too late for an eclipse because we turn about 19 degrees on that plane there. Okay, just a little bit of knowledge here. Perihelion is the closest point of the Earth to the Sun. See, the Earth also has a very slightly elliptical orbit around the Sun. closest point to that ellipse is called the perihelion, the farthest point is called the aphelion. With the moon, we use a different terminology. The closest point is called the perigee, and the farthest point is called the apogee. And I'm mentioning it now because I might refer to those words, so I'm hoping you remember that part. Now, here's an example that shows you the dotted line there around the sun in the middle is what the Earth's orbit would be if it was a perfect circle. But in reality, here's the perihelion, so the orbit of the Earth comes inside that perfect circle now. And when you get closer, when you get farther from the sun, you're aphelion now. You're outside that circle and you're farther away. Now, likewise, the outside dashed line there is what the moon's orbit would be if it was circular. Now, the moon's orbit is elliptical, and it's a lot more elliptical than the Earth's orbit is around the sun. So the position of the perihelion is actually quite a bit closer than the aphelion, and that explains why I think more than half of your eclipses are actually annular versus total eclipses when you get an eclipse of the sun. But not by very much. You do get almost an even number of each. Now, one other thing I should show you here too. Well, I'll wait till I get to another slide. Okay, well, I'll mention it now. Now, I hope you can see this. This is an exaggerated, that black dot there is supposed to represent the Earth. And this outside ellipse here is supposed to represent a highly exaggerated version of the moon's orbit being elliptical. But what happens is that the plane of that ellipse, like remember we said that the plane of the Earth-Moon rotates gradually, it shifts about 19 degrees every year. Well, the perihelion also rotates, but it goes anti-clockwise like this. Imagine there's the Earth in the center. So the perihelion also has a circuit, and that one takes 8.85 years to go around. So you can see here we've got the nodes that have to line up with the sun and the moon. That's the one thing that determines whether you get an eclipse or not. But if you're going to get similar eclipses, we want to find, is there any cycle where sometime in the future the exact position of the perihelion and the exact position of the nodes will line up. And that's what these Saros cycles are all about. Okay, just here's an example of when I was trying to show you on the little ellipse there. This is what actually, although this is like is a representation of the Earth going around the sun, it is the same direction. If you imagine the Earth is in where the sun is, and the rotating body is the moon, very exaggerated, of course, but that gives you an idea what happens to the ellipse, how the orientation of that ellipse changes over time. It takes 8.85 years to do a complete circuit. So we've got a lot of different motions happening. Now that picture is an example, that will be coming to the end of an eclipse. And then the very first thing you'll see is when the sun starts to appear, we've got what we call like the diamond ring. It almost looks like a ring with a sort of stone in it. And that's the first sign that the sun is going to reappear. So if you are watching the sun when it's totally covered, which we can't do from Winnipeg because we're not getting a total eclipse, as soon as you see the diamond ring, you have to look away from the sun right away. Because any moment after that, you're going to see the sun start to shine on there, and that could damage your eyes, see. Okay, that's right, yeah. Okay. Now for a little bit of historical perspective here about cycles. Now the Chaldeans were people who lived in southeastern Babylon, and they kept very, very good astronomical records. And it wasn't just one person doing it. They kept records from the 9th to the 6th century BC. So generation after generation after generation, they were studying lunar eclipses, because you could see lunar eclipses when they happen, as long as you're not in sunlight at the time. And they were able to see that after many, many years, there did seem to be kind of repeating patterns. And that really blows me away that people, you know, back then, with their technology, were still able to figure that out. And in fact, they were able to recognize at that time an 18-year cycle. I mean, when I say 18 years, 11 days, and 8 hours, that depends. If there's 2 leap years, it would be 18 years, 10 days, and 8 hours, say. But either way, it's best to express it in days, because then there's no confusion. And that eclipse cycle, and we will explain how that cycle pops out in a minute here, but that's been recognized since antiquity. Hipparchus and Ptolemy and all the others, they knew about this too. So, I mean, this goes back way, way long. People have been studying this. It's only today that we don't really have the time and cell phones to really study all these things, you know. And what they discovered was that evidently eclipses with similar properties. Now, when we say a similar type of eclipse, was it annular? Was it total? Is the length the same? Is it roughly in the same part of the world? Is it roughly in the same latitude? These are the kind of things we're talking about here. And they noticed that after those 18 years, 11 days, 11 1/3 days, I should say, and that's important as well, things did seem to repeat. And I'm amazed that they were able to do that. But the name Saros cycle didn't exist until Edmund Halley coined it, back there in 1661. And that name actually came from the ancient Babylonians, Saru, which meant 3,600, like a tenth of a degree on the circle. I'm not sure what the significance of that is, but it was Edmund Halley who started using the word. This is the Saros cycle eclipse, and that word has stuck ever since. So here's an interesting picture there of an annular eclipse. Now what has happened, I think there, the top picture here, the moon was crossing it from the east, like it's setting, so the moon was coming this way. And then later they snapped another picture when the sun was here, and they got the annular eclipse. And then after the moon started moving off, they could sort of capture that. But what a sight, eh? That to me is more impressive than a fully total eclipse. Okay, so in order to understand these cycles, now, if we have an eclipse of the new moon, it's 29.5 days, basically, for the next new moon. So we have that cycle. Every 29.5 days, we have a new moon. And we have to have a new moon when we have an eclipse of the sun, because the moon has to be lined up with the sun and the earth. Now there's another cycle. When we talked about, the rotation of the ellipse, we're talking about there perigee to perigee. In other words, when it goes from this point to that point again, it's done one complete circle. The month for that is 27 days. Now, you might say, well, 27 days and the new moon to new moon is only 29 days. And I said it was a really slow-moving one. But what you have to remember is that when you, let's say you get the eclipse of the sun right now, there's the nodes lined up. The Earth is going around the sun. And when you get the next new moon, the axis of the nodes hasn't moved very much, whereas the sun is over there now. And that's why it only takes 27 days for one of those cycles, whereas you have to wait the extra 29 days before the nodes will line up with the sun and give you a new moon again. So that's why there's a big difference there. So you've got the perigee cycle, and then you've got the plane of the moon, the plane of the Earth moon itself. Remember we saw that picture of the red disk flopping around, and I was trying to show the cycle? A draconic month, as it's called, like node to node, is 27 days and 5 hours. It's only 8 hours different from the perigee to perigee. Now that doesn't mean much by itself, but the definition of a Saros cycle is 223 synodic months. Like this is a synodic month, new moon to new moon. So every 223 new moons, it happens like every 18 years, 11 days, 11 and a third hours, eh? But also, 200, okay, that's the expressive days. It's 5,685 days, and just short of 8 hours. It's not quite 8 hours, but it's pretty close. And that's only about 0.02% difference or something ridiculous, eh? But the other cycle as well is the anomalistic month, which is the perigee to perigee. And you can see that in the time that we had 223 synodic months, if we have 239 anomalistic months, look how close they are. They're only a few hours difference, eh? Both of them are 6,585 days, one's 7 hours and one's 12 hours, or 13 hours. So there's only about 5 hours difference between those two. And by a wonderful coincidence, the draconic cycle, you can get 242 draconic months in that time. And that turns out to be the same thing, but it's only about 52 minutes different from the synodic month thing. So you can see that what a fortuitous coincidence. Everything is all lining up after 223 new moons, if you like. Even though it takes 18 years, 11 days, and 8 hours for that to happen. Now, because of that, now at each time you have a Saros cycle, and everything's all lined up again, the fact that you're 8 hours different from the previous one, it means a similar eclipse will happen 120 degrees around the world to the west. And then, because of those 8 hours. So if you take 3 Saros cycles, it should be back pretty well to where it started. But I mean, 54 years is a long time to take the measurements, see? Now again, we're showing this one again, because just to mention that the nodes regress westward by about 19 degrees a year. I think we mentioned that already. Okay, now I think there's a mistake here in the literature. Because if you can imagine, let's say, I wish we could stop this right now, but during the full eclipse. A couple of minutes, okay. Okay, we'll just get past this Saros stuff then. Now, if you can imagine, I was looking at this and I was trying to figure, well, what are the eclipses going to do with this? But the interesting thing is that after 223, what I call new moon months, the synodic month, after that time, because all those parameters weren't exactly lined up, after one Saros cycle, it'll be shifted a little bit, which means that any eclipse in that Saros, every time the Saros cycle repeats, you get another eclipse in that Saros cycle. And those Saros cycles can go on for centuries. But because there's a slight discrepancy in how things line up, eventually there will come a time when the node will drift sufficiently that you will no longer get those eclipses. Eh? And just as the nomenclature, we call odd Saros numbers when you have ascending nodes and they're even when you have southern ones. Now it's a little hard to understand about why the eclipses run from north to south. If you can imagine that after one complete Saros cycle, the node is actually shifted, I think it does actually shift east, not west. So in other words, as the moon starts coming down here, it comes across this way. Each cycle will be a little bit further west. That way, when the moon comes down here ahead of time and eclipses the bottom part of the sun, it means that the shadow of the moon is now going to be underneath the Earth, on the bottom part of the Earth. And each successive eclipse that comes across from the west, it means that each eclipse will move up the Earth's surface. And when they disappear off the top of the world again, that's the end of your cycle. And when they start at the bottom of the world with partial eclipses, that's the beginning of each cycle. So even though you get eclipses, a few times a year, so to speak, The Saros cycle is only interested in the eclipse that comes back in the cycle 223 new moons later. So that is basically what the Saros cycle is all about. And this is an example of how the Saros circle would actually work. It would start coming in here, so the shadow would be below. No, actually, it would start here, sorry. It would start here, coming in from this angle, from an ascending node. Eventually, it would cover the moon, we get a few good eclipses, and after that, you get partials towards the end of the cycle. But that cycle can last anywhere from 13 to 15 centuries. So it's a very, very long cycle. There it is, 1200, 1300 years, and you can probably get anywhere from 69 to 87 eclipses in any given cycle, which 43 of them are central. And when we say central, it could be total, it could be annular, or it could be a hybrid of those two. But that's what we talk about when we say that 43 of them are central there. And in any given time, there's probably 40 different Saros cycles going on. That's why you can get more than one eclipse every 18 years. Eh? And right now, the active series in the Saros series, anywhere from 117 to 156, they're the active Saros numbers that are taking place at this point in time. And in fact, the eclipse next month, it's in the Saros cycle 145. Yeah, so we already mentioned this about the longitude being displaced there because of the 8 hours. Well, I think that's probably all we've got for now. I know Brendan was saying that we've got to shut it down. But I hope I've given you some insight, at least, to what's going to happen on the 21st of August, what causes an eclipse, and if you look at the different cycles, like the monthly cycle of the new moon, the monthly cycle of the elliptical orbit, the way it happens, and also the plane of the Earth-Moon, how that rotates as well. What basically happens, if you can find, like the Saros cycle, where all things seem to come together after so many eclipses, then you can actually get a pattern. So I think we'll stop it there, because I think I'll probably carry on with the next, maybe a couple of meetings down the road there and go into more detail with the cycles. But hopefully this has given you just a bit of insight as to what causes eclipses and how there is some kind of pattern to them, even though in one lifetime it's impossible to recognize. So don't expect to go and find that by looking at eclipses, because you're just not going to see that cycle. But it is interesting, and you've got to live an awfully long time to see these things come back all the time. So I hope you enjoyed it, and
Okay. Thanks a lot, Mick. Just one small piece of errata. I think Mick may have misspoke, but there is another total eclipse coming to the continental United States in 2024. Yeah, it should be 2024. So, yeah. So, anyway, just want to clear that up. Okay. So, maybe. Hopefully we all are. So this got turned around a little bit. Obviously, the approach break it. We're kind of doing this backwards, almost, or I don't know, some kind of weird pattern to that. It's the Saros cycle of okay. So what we're going to do is I'm just going to run through some announcements, and then Danielle from the University of Manitoba is going to give us what's new in the science of astronomy. So real quick, I just wanted to run through a couple of volunteering and outreach opportunities. So we have one coming up Saturday, July 19th. This was, we actually got contacted on the website about doing a small little start party. And Mike Caracas, Mike, are you here tonight?
Yeah, I'm here.
You're here? Okay, great. Yeah, so have you heard anything else about like how many people to expect or anything like that? Or
Not really, actually we might do a solar event during the day,
Okay.
and then follow with an evening event afterwards.
Okay.
And it's the 29th as well.
Oh, did I have the day wrong?
Yeah.
I'm sorry. It's
No
the
problem.
29th. Okay. So, thanks, Mike. Yeah. So Saturday 29th. It's in the White Shell. But yeah, if you'd like to come and volunteer, you don't even need a scope or anything. It would help if we had one, but even just some people around to help out would be nice. And just contact myself or Mike. And you can contact me through the website if you're interested in volunteering. So, this date, I know I have right. There's a solar eclipse in Winnipeg, and nobody's going to be here because we're all going to be in the States. But for anyone that's sticking around, I've had a few places asking me for help. Bristol Park has asked for some assistance. Scott has definitely been asking me for some assistance as well. Anyone around? It's the middle of a work day, so I can totally understand. If you could come by the planetarium just to help out a little bit with the throngs of people. And that sort of, even just crowd control, I think would probably be greatly appreciated. So you don't need a solar scope, you don't need to have any solar glasses, nothing.
We will provide you with solar glasses. We have 11,000 pairs that we're still eagerly waiting for. And we will also have 6 or 7 solar filtered scopes out. Unfortunately, we expect most of Winnipeg will probably show up at key times. So the more the merrier.
Yeah. So yeah, but if you'd like to help out, I think at this point you could probably just show up. But you can contact myself if you want more information or details or anything like that. Yeah, but please, if you are in the city and you can find some time to help out, please do. I really appreciate it. So, I'll bring you back something nice from Nebraska. Yeah, I'll get you some corn. Okay, we do have eclipse classes. National did put a stipulation on this. They are not for members. But if you're willing to distribute to the public at about, say, 1 per family, that's totally fine. We've got some here that I'll hand out after the meeting. There's a limited number of them, so again, it should be about 1 per family that we want to try and do. And so, this will be for situations in particular. If you're back in Winnipeg, if you're at work, and you just want to show people the eclipse, take a couple, kind of thing, right? So if you're willing to do that, that's a good measure of outreach. And yeah, so what'll happen is I'll just set up after the meeting here, and you can just come grab them, kind of thing. Okay. Telescope loans. This is managed by Stan Runge, not the asteroid, the person. He is not here tonight, but he does manage our telescope loaner program. So if you are a member, it's one of the perks of being a member. And if you're not a member, you didn't sneak in. It was totally cool if you were here. These meetings are always free and open. But if you want to think you snuck in, that's cool too. If you are a member, you gain access to some loaner telescopes. There's an 8-inch job. I think there might be a C8 in the mix now. There's the solar telescope, which won't be available for the eclipse. And yeah, it's a good opportunity to get out under the night sky. You can borrow a telescope for a month, and then see how things go. So it's a good way to get your feet wet. So I do recommend checking that out. If you'd like more information, the easiest way to do it right now is probably to just contact Stan through the website. There's a contact form. Just select the option for telescope loans, and you'll get an email about it. On the observatory, if you are a member, you get access to our observatory south of the city. Brian Statch is the guy who runs that. So if you want to, you can see him. I don't know where he's at. But...
Over here.
Oh, hi, Brian. Yeah, go back, Brian. You can get your key. What else? Yeah, members observing night. So Brian, being the Lonely Observatory Director, has scheduled a members observing night for Saturday, July 22nd. And again, I'm pretty sure I have that date right. Who knows? But pretty sure I got that right. I think it's next Saturday. So, so that'll be held at the Lonely Observatory. So that's for members only. In conjunction with that, the Explore the Universe program. Dennis, do you want to say a few things about that? Right.
Can everybody hear me? Okay, so first off, how many people here know about the Explorer of the Universe certificate by the RASC? How many people here have actually completed it?
Don't look at the stage.
Not very many. What we're trying to do is we're going to run on during the Observer's Night, set up so that we can help people earn that certificate. Okay? So it gives you another reason to come out for Observing Night. We'll work through the program. We'll take it whatever we can because it's based on season. For any of the new members or anybody here who's new to the group, you don't need a great big telescope. If you've got a good set of binoculars, you can still earn the certificate. So just because if you don't have a scope, don't let that hold you back. Come on out. Come out, see what's going on. Participate. We look forward to seeing you all out there. If you have any questions, you can track them down. Thanks, Ryan. Ryan?
Okay, thanks, Dennis. Okay. Now I have a special presentation. So I joined the Winnipeg RASC back in 2009, I think it was. And yeah, I'm so old. Not seriously. And when I first joined, it's a very welcoming club. You know, people get excited about astronomy and they're enthusiastic and they want to talk about it and they want to share that love of astronomy with you. Right? And that's really cool. And that really drew me in. I met a lot of cool people. I can name them, a whole bunch of them. But there was one person who really did stand out. Your mic.
Mic's off.
We have to take this out. I think my battery might be down. Hold on. Was it back on?
Yep.
Yeah. I don't know if it's gonna last. Can you hear me now?
Yep.
Okay, cool. Now we can talk both ends. Cool. Okay. So as I was saying, there was one person who stood out quite dramatically. I remember my very first Sprucewood Star Party. I showed up and found out that I had my tent, but my tent poles I had left at my parents' place in Kenora from the last time I went on camping. So I showed up and tried to set up my tent and realized I had nothing. This is great. And so I went to go talk to somebody about it. Just a tall, friendly individual with long hair and a beard. And he walked me around. He walked me around and showed me and just introduced me to a bunch of people that I had only been with the club for about 3 months at that point. And yeah, he showed me around and he introduced me to everyone. And later that night, we hung out for hours and hours and hours, just looking under the night sky. And I can tell you that this guy has done an immense amount for the club, and he does these binocular tours at Sprucewoods that if you haven't experienced, you really need to. You really need to. They give you a fantastic perspective on space and everything around it. So, Jerry, do you want to come up here?
Oh, jeez.
You can't say no to that. Yeah. He also looks very presidential. like Matt. That's not him. I don't wear a tie, but I know how to tie one. Okay. Anyway, so I'm just going to read to you what was written by I believe somebody in the Winnipeg RASC. Jerry Sperchansky is a bit of a I can do that normally. Sperchansky is a bit of a legend around southern Manitoba for his indefatigable efforts to spread a love of astronomy within the community. He has been a member of the team from the Winnipeg Centre helping Riding Mountain National Park, Spruce Woods Park, and the Nature Conservancy's Weston Family, Tallgrass Prairie Interpretive Center obtained dark sky status. I said that terribly, but there's a nature conservancy that we've been working with, and Jerry has been very instrumental in helping us get dark sky status down here. Projects that will soon be implemented. As a result of the efforts of Jerry and others, Spruce Woods now has a telescope to use. Jerry seldom talks about himself and his activities unless pressed. He is a favorite son of the Winnipeg Centre, never without a moment to help with a problem, as I noted, or share an amusing anecdote. He always reminds you about the 10 holes, or consume a jug of beer. It is with an amazing amount of pride that, Jerry, I present you with the RASC National Service Award. Schmaltzy stuff out of the way, we are going to move to Danielle to do what's name.
Can everybody hear me in this volume? For those of you that don't know me, my name is Danielle Hood, and I'm an instructor at the University of Manitoba and director of the planetarium there, although it's shut down for some maintenance. So today I have the pleasure to tell you about some of the new developments in astronomy over the course of the last month or so. So I'm going to be starting with the very first observation of a binary pair of supermassive black holes. And this was published in a paper at the end of June entitled Constraining the Orbit of the Supermassive Black Hole Binary 0402 plus 379. And that is a numerical name for an elliptical galaxy that's fairly far away. So the authors here, and this was published in the Astrophysical Journal. And so here the image I have up is an artist's conception of two merging black holes with swirling gas around them. But let me unpack what this observation means and why it's surprising or interesting that this is the first observation we have. So this is a gorgeous shot of the Andromeda Galaxy, one of the large spiral galaxies near our own Milky Way, as Scott was showing us earlier today. And we know that at the center of most galaxies, there exists a supermassive black hole. And so supermassive black holes aren't necessarily rare. different phases of collision. And so these collisions aren't rare, and we know that at the center of each of these galaxies, there is a supermassive black hole. And so we expect these supermassive black holes to be somewhere in this tangled mix, but we're not exactly sure where, and it's hard to observe a black hole directly. Usually you have to observe it by looking at the motions of things around it, because black holes effectively suck up or don't emit any light. So you have to infer their presence. This, unfortunately, is a PDF screenshot of what would have been a computer simulation movie. And so the blue are the stars, the yellow is the center gas, and you can imagine in your head these two galaxies orbiting around each other and passing through. And as they pass through, you get this gorgeous spray. So the blue ends up kind of creating these spiral wisps, and the yellow cores eventually settle and merge. And so the black holes, the supermassive black holes, are right in those yellow cores. So the supermassive black holes for each of these galaxies should, theoretically, be near each other. And eventually, perhaps, orbit each other. And so we've observed some supermassive black holes close to each other, but never really close, or close to merging. Until this paper. So we have observed a grand total of one close supermassive black hole pair. And it's at the center of this elliptical galaxy, 0402 plus 379. These two black holes are only 24 light years apart. And so this is within that communication sphere that Scott was showing in our life video, right? If these had been radio waves, these two black holes would have been able to talk to each other since humans have had radio communication. They're at a redshift of 0.05, which is astronomer code for distance. So 242 megaparsecs away from Earth, so quite a distance. And the image I'm showing here, and I'll come back to it, are radio jets coming off of the black holes. Most black holes have magnetic fields wrapped around them and hot gas that have free electrons in them. And the electrons orbit around a magnetic field, and moving electrons will create radio signals. And so if a black hole has a jet coming off of it, you can observe the jet in radio. And so these blue, do we have a laser pointer?
Yes, the top button.
Top button. There you go. Okay. So these are jets, and these two are what they think are the hot disks around the base of the jet, so around the black holes. This was detected using the Very Long Baseline Radio Array, or VLBA, which is a series of radio antennae scattered smaller than the supermassive black holes I was talking about earlier. These are a more modest 31 and 19 solar masses respectively. They combined to make a 49 solar mass black hole. And I'm not bad at arithmetic. It's that the difference in mass got converted to energy into these gravitational waves. And so the fact that we've observed 3 of these mergers within the past year or so tells us that this class and this mass range of black holes is fairly common, which is news to astronomers. This is also the first observation where we think that the spins of the black holes weren't completely aligned. We had to talk about orbits and orbital planes. So if you think of the 2 orbital planes of black holes, if the black holes started as binary stars and collapsed together or at about the same time, then their spins would be roughly aligned. And so the fact that these 2 aren't would suggest that perhaps one black hole formed at one time and then either captured another one or captured a star that then became a black hole. The other thing is that the distance to this merger was much further, about twice as far as the previous 2. And that allows us to detect whether or not wave dispersion is happening. And so wave dispersion is when waves of different frequencies travel at slightly different speeds. And so if you have a wave of a higher frequency arriving a little bit sooner than a wave of a lower frequency, that is dispersion. And so Einstein predicted that dispersion would not happen at all with gravitational waves. And the nice thing about dispersion is that the further something has to travel, the more time the physical effect of dispersion has to act. And so the larger the time difference between the highest frequencies and the lowest frequencies. And so this merger being further away gave us a really good rigorous test to see whether or not there's any dispersion in the gravitational waves. And there was not, which proved, or at least supported Einstein's prediction once again. Here was a schematic I thought was really interesting. So we are here. These are circles, concentric circles, in units of billions of light years. So the first black hole merger occurred 1.5 billion light years away. And the total merged mass of the black hole was 62 solar masses. The second one detected, which was much less massive, it was 13 and 8 solar masses. And this third one was 3 billion light years away, so much further. But this is kind of where these things have been detected, how far away. And they're all in the same plane. We can't pinpoint exactly where they are because we only have 2 laser interferometers. One in Louisiana and one up in the northwest, I forget. Washington. And so you can kind of tell, if it hits Louisiana first and then Washington, you can tell them we're just kind of in that general direction. But you can't get a lot more specific. So they're building a 3rd interferometer in Italy to help pinpoint where these things are coming from. Okay, I'm going to take a sip of water and then we're going to change topics. We heard about finding planets outside of our own solar system, but we are still finding planetary type masses inside of our own solar system. And so catastrophic that flew by but was just a one-time thing. And so there are some hypotheses that a small star may have whizzed by our solar system, perturbed these Kuiper Belt objects just once, and it was about 10 million years ago, so fairly recent, and that we're still kind of settling down from the effects of that disturbance. But the authors note that's less likely of a scenario. All right. The last of my astronomical news is that there is a new class of variable stars, and they are called the blue large amplitude pulsators, or BLACs. Astronomers are real good at acronyms. There have been 14 of them discovered so far. They've been discovered by a large general variable star survey called OGLE, which is actually a pretty on-point acronym. I like that one a lot. And so these variable stars actually vary a lot in brightness or magnitude. And so the amplitude of the variation of their magnitude is between 0.2 and 0.4 magnitudes. And that amplitude is very consistent for each of those 14 stars. So depending on what physical mechanism is driving the variation, the amplitude of the brightness change can vary, but in these cases it's very steady, which tells us that the thing that's driving the variability is a very stable process. The period is very fast. Things cycle through a dim to a bright back to a dim point in 20 to 40 minutes, so under an hour. So whatever is driving this variability is happening on timescales that are very short. There's a slight color variation with the brightness variation. And so what that tells us is that the temperature at the surface of the star is changing. And using a method called spectroscopy, you can look at the color of a star, and that will tell us what the temperature at the surface is. And so we can tell that the surface temperature of the star varies between 28,000 Kelvin and 33,000 Kelvin. And so that surface temperature tells us these are hot blue stars, and they're fairly small. We can deduce from their brightness, so they're blue subgiants. The correlation between the temperature and the color changing tells us that they're pulsating in the fundamental mode, and what that means is that the entire star is shrinking, heating up, and then the extra heat causes it to puff up again. As it puffs up, it cools down, gets dimmer, and then as it cools down, it starts contracting in on itself, heating up, gets brighter, and it does this over and over again every 20 to 40 minutes. The light curves have a characteristic sawtooth shape, so they rise really quickly, they get bright really fast, and then they slowly decay, and then they get bright really fast, they slowly decay. And so this is characteristic of stars that do pulsate in the fundamental mode. So this contraction, and then a rapid expansion, and then a slow contraction again. Using spectroscopy, we can tell that these stars have a rich hydrogen atmosphere, and so they're likely burning helium at their core, similar to a subdwarf, so a relatively small O or B type star. But they have a much lower surface gravity, which we can also tell from spectroscopy, which tells us that they have very puffy outer envelope. So whatever they are, they're hot, they're puffy on the outside, they're burning helium deep in their core. And so the candidates for types of stars that these may be, or the progenitor stars for these, could be something that has a zero age main sequence star mass of 5 solar masses. So that means the star, when it was first born, was 5 times the mass of the sun, and it's burning helium in the core, but it has a layer of metal somewhere in the middle towards the outside. The metal doesn't conduct heat the same way that the hydrogen and helium does, and so the metal, will trap the heat for a while, and then they will drive the heating and contracting. And so in this case, it's really just the outer layers of the star that are puffing up and contracting and puffing up and contracting. And coming months, we'll find more of them and get a better understanding of exactly what's driving the variability. And that's all I have.
Any questions?
Any questions? Yeah.
For submersion, black holes meet each other time. There's only one wave that we can detect, and then it's done. Or does it leave many ripples?
So there's kind of a wind-up. So the signal for merging black holes starts off as a wave that undulates fairly slowly and then speeds up. So if you think of try and think of a good analogy. There's a gravitational well out in the play area, right, where you drop a penny in. And when it first starts, you know, the two black holes are orbiting, and they're orbiting fairly slowly. But then as they get closer and closer to each other, they're going to start spinning up, and eventually when they merge, it kind of pops. And so the wave signal that we see, I'm going to do this. I'm going to be a little embarrassed. But if you were to sonify it, make it a sound, it kind of goes, whoop. And so you start with just like that. So it starts with like a low frequency signal that accelerates. You get something that, I don't know exactly how long those signals last, but they don't take a ton of time to propagate over the Earth. So
that signal from the low frequency to high frequency, this is a whole event.
yeah,
Encapsulated.
yeah, yeah.
It's really quick.
Yeah. Yeah. I mean, if you were to think of dropping a rock into a very still pond, there would be a whole series of ripples that propagate outwards, but there would be like one ripple that was bigger than the rest of them, right? And so even though there's a whole series of waves, you kind of start getting the low, like, precursor ripples, and then a big one, and then it kind of dies out. And so it's not a perfect analogy, and you can get a wave, but the signal itself is fairly short-lived.
That picture showed when the three black hole mergers from the LIGO data.
I think it's due to the placement of where LIGO is, right? So we have two detectors, and so we have it, so like, I think on the last one we observed it in Louisiana a minute and a half change in magnitude is rapid and large. And so you would expect it to be quite easy to find, a bright star that's varying a lot within an hour. My astronomy class could probably pick that up.